Hey everyone, welcome back. In this video, we are going to continue our review of piecewise functions for AP Calculus. Specifically, this video is going to focus on continuity. So let's go ahead and jump right in. So first thing you need to know are the three requirements or checks that you must do to see if a function is continuous at a point C. They are listed here, 1 through 3, and let's go through them one by one. So the first is that f of c must be defined. What that means is that it means that there must be a defined output value for the given input value of c. So let's just do a quick little illustration of that. Basically, if you had a graph that looked like this, where of course this was your c value, f of c would not be defined because of those two open circles. However, if you were to include a point here like that, then f of c would be defined because you have an output value for that input value of c. Okay, so let's move on to number 2. Second requirement is that the limit from the left must equal the limit from the right, which is going to mean the overall limit exists. That's super important. So for the overall limit to exist, the limit from the left must equal the limit from the right. Then the third requirement is that all three of those things must equal each other. So limit from the left must equal limit from the right, must equal the function output value. So again, let's say we had a function like this. So the limit from the left would be here, the limit from the right would be here, and then it must equal the function output value, right? So that would make the function continuous at that point C. So let's go ahead and take a look at an example of a continuity check to kind of pull all of this together. So basically here we have this piecewise function f. You can see we have two function rules, this one, and then over here on the right, it tells us when to use each one. So for piecewise functions, oftentimes you're going to be asked whether the function is continuous, where these boundaries are changing. Just kind of something interesting to keep in mind. So as an example, if we want to determine if f of x is continuous at x equals 3, what would we do? First, we would check, is f of 3 defined? So we would be using this function rule because this is defined for x is less than or equal to 3. And we would see that it is, right? We would just plug it in right here and we would get 4. So our first piece of information would be that f of 3 equals 4. Second, we would have to take the limit from the left and then the limit from the right. So the limit from the left is going to be using the top function rule, because if you think about these x values, right, if we just think of a quick little graph, the x values 0 to 3, let's say this is 0, 3, and 5, right? So if we're coming at it from the left towards 3, we're going to be using that top function rule that's defined for these values, the values less than 3. So the limit from the left, we would just plug in 3 for x and we would get the same thing of 4. Now we have to check the limit from the right, which again would be the values that are greater than 3 coming from this side, right? And so if we were to plug in 3 here, just directly substitute that in, we would get 2. So now, are the limits from the left equal to the limit from the right? Well, in this case, it is not, because limit from the left equals 4, limit from the right equals 2. Therefore, we can conclude that this function is not continuous at x equals 3. All right, now let's go through some multiple choice questions to make sure all of these concepts make sense. So, first question, we're given this function here, and we need to find if f is continuous when x equals 4. So we're going to go through the three requirements for continuity, starting with, is f of 4 defined? So in this case, we see that it is defined because this top function rule is defined for x is less than or equal to 4. So let's go ahead and plug in 4 for x to get the actual value. So in this case, we would get 9. So f of 4 equals 9. Now let's go ahead and take the limit from the left and the limit from the right. The limit from the left is again going to be given by this top function rule. So of course, using direct substitution, I'm going to get the same thing. So limit as x approaches 4 from the left is also going to equal 9. Now, I'm going to have to take the limit from the right, which is where I use my bottom function rule. So here I'm going to be doing limit as x approaches 4 from the right, and then I'm going to do direct substitution. So 5 minus 4 is equal to 1. So again, in this case, we would say no, the function is not continuous because f of c does not equal the limit from the right, does not equal the limit from the left. All right, moving on to question number 2. So now we are looking to see if g is continuous at x equals 2. Let's start it off same way. Let's go ahead and get g of 2. So in this case, we are going to be using the second function rule because here it's x is greater than or equal to 2, for which the second rule is defined for. So we're going to go ahead and directly substitute that in. We're going to get 6 minus 2, which is equal to 4. Now, let's go ahead and take a look at the limit from the left. So we're going to be using the top function rule for that. So we're going to go ahead and direct substitute into there, and we're going to get 2 times 2 minus 1, which is 3. So again, we already know this is not going to be continuous, but I'm going to go ahead and write out the limit from the right just for the sake of it. So that's 6 minus x. Doing direct substitution, I would be doing 6 minus 2, which is equal to 4. So again, is g continuous at x equals 2? No. All right, moving on to question number 3. Is h continuous at x equals 1? So again, to get h of 1, in this case, we are going to use our second function rule because this is defined when x is greater than or equal to 1. And let's go ahead and do direct substitution. So 3 times 1 is just 3, minus 1 is 2. Now, the limit from the left is going to be given by the top function rule. So using direct substitution, I'm going to do 1 squared, which is just equal to 1. So again, we've already seen here, this is not continuous, so we would say no. Just for the sake of it, I'll go ahead and write out the limit from the right as well, which again would be direct substitution into my second function rule. So I would get 3 times 1 minus 1, which is the same as my output value of h of 1, which is just going to be 2. All right, moving on to question number 4. Is j continuous at 0? This one is kind of fun. It's a little different because now we just have wider intervals. We actually really just have open intervals rather than the ones that were above. So first things first, what is j of 0? Well, in this case, we would use our second function rule because x is greater than or equal to 0 is where it's defined for. So using direct substitution, we would do 0 squared minus 2, which is just equal to negative 2. Now let's take the limit as x approaches 0 from the left, which is going to be given by 4x plus 3. So it's going to be 4 times 0 plus 3, which is equal to 3. And again, this is not going to be continuous, we already know, but let's go ahead and check the limit from the right, which is again going to be the x squared minus 2, which is going to give us the negative 2. Kind of speeding through that because we already know it is not continuous. Okay, finally, let's check k, where x equals 1. So k of 1, we're going to use our bottom function rule again, and using direct substitution, we're going to do 1 plus 1 squared is just 1, so 1 plus 1 is 2. Now, let's go ahead and do the limit as x approaches 1 from the left, which is going to be given by 2x. So we're going to do direct substitution. 2 times 1 is equal to 2. Okay, that looks good so far. Now, let's go ahead and check our limit as x approaches 1 from the right. So that will be defined by our bottom function rule, or our second function rule, which is 1 plus x squared, which is going to give us 1 plus 1, which is 2. So finally, we got an example where we would say, yes, k is continuous at x equals 1 because k of 1 equals the limit as x approaches 1 from the left equals the limit as x approaches 1 from the right. I didn't write k of x here, I really should have. I was just being a little quick and just kind of lazy with my notation, but really I should write the limit as k approaches 1 from the left of k of x, and same thing for obviously as x approaches 1 from the right. All right, thanks so much for watching, and I will see you in the next video.